Hello everyone. In this video, I continue talking about supply chain management. In the previous video, we just talked about transportation and transshipment problems. These problems are macro level problems. At the micro level, also deliveries to customers should be planned carefully because efficient delivery schedules have an important impact on the design of the entire supply chain. And finding the optimal delivery schedules is not so easy. In fact, they are very difficult problems in general. And delivery schedules are closely related with a popular problem called traveling salesman problem. Now I will talk about traveling salesman problem. In this problem, there is a salesman and salesman has to visit a number of customers, for example, end customers. The aim is the aim of the salesman is to leave his or her home, visit each of the customers, and go back to his or her home. And while doing this, the main objective is to minimize the total distance traveled. For example, in the first figure, we see a possible solution for this TSP problem. Here you see the route. And here we have a second possible solution for the same problem. In fact, the definition of the problem is really simple. And when n is small, I mean the number of customers visited is small, it is possible to enumerate all the routes and check find the one with the least cost, and we can find the optimal solution. For example, when n is 5, when the number of customers is 5, there are totally 120 different routes, and we can easily check the cost of these routes and find the one with the minimum cost. But when n is 10, I mean I only double the number of customers. As you can see, the possible number of routes becomes more than 3 million. Now, in this case, it is not so easy to calculate the cost of all these 3 million routes and find the minimum one. So you can see that when n increases, it becomes impossible to solve this problem with total enumeration. We call this kind of problems as NP-hard. NP stands for non-polynomial. This means that the solution time of the problem increases not polynomially, increases exponentially, as you can see in this example. For example, when n is 25, also this is not a huge number for a real life case, because a company may have more than this number of customers, probably. When n is 25, the amount of possible routes becomes 1.55 multiplied with 10 to the power 25. I would like to show you how large this number is. For example, you have a supercomputer, and with the supercomputer, you can evaluate 1 trillion routes per second. And with this supercomputer, if you evaluate all possible routes, then it would nearly take 500,000 years to evaluate all the sequences. So this example clearly shows that with total enumeration, it is impossible to find the optimal solution. But there are very different methodologies developed to solve traveling salesman problem, but it is still difficult to find the optimal solution even for moderate-sized problems. In this lecture, we will not concentrate on solving the traveling salesman problem. Now I will introduce you another problem, vehicle scheduling. In fact, this vehicle scheduling is also related with TSP. In vehicle scheduling, there is a central depot with one or more delivery vehicles and end customer locations, each having a known requirement. And in this problem, the question is how to assign vehicles to customer locations to meet customer demand and satisfy weather constraints there might be at minimum cost. In real life, vehicle scheduling problems are too large and complex to solve optimally. Here we have the central depot, we have end customers. If we have a single vehicle, in fact the problem is classical traveling salesman problem. But if we have more than one vehicle, then you see that we have to determine different rules for each of our vehicles. For example, if we have 4 vehicles, one possible solution for this problem is shown in this second figure. Obtaining optimal solutions for vehicle scheduling problems is not easy. For that reason, to be able to find good solutions are also important. And now I will introduce to you a simple method called savings method to solve vehicle scheduling problems. This is not an exact method. I mean, we are not able to find the optimal solution with this methodology, but we are able to find a good solution for vehicle scheduling problems. Now, according to this method, in our problem, we have a single depot and all the vehicles depart and return to this depot. We know the location of the customers and we know the needs of the customers. We identify our depot as 0 and we locate the customer from 1 through n locations. And we know the cost of making one trip from the depot to each of the customer, and we call this as C0J. Moreover, we also know the cost of making a trip from customer location I to customer location J, and we call this as Cij. And we assume that Cij is equal to Cji. Of course, in all situations, this may not hold. For example, if there are one-way streets, the Cij may be different than Cji. But for this methodology, we assume that Cij is equal to Cji. And here, for this method, we assume that initially we assign n vehicles for n customers. So we create n routes for each of the customers. So in fact, each vehicle visits only one customer and then turn back to the depot. And for this initial solution, the total cost is C0J, I mean the cost of traveling from the depot to customer J. We multiply with this 2 because we go and come back to the depot and we assume that Cij is equal to Cji, and we sum over all the customers. And this is our initial cost. Now we will consider what would happen if we link the customers. For example, assume that if we link the customers I and J, what would happen? Now, if we link the customers I and J in the same route, then we will save a cost of C0I and C0J because when they are in the same route, now we disregard a trip between the depot and location I and also a one trip between depot and location J. These are the savings, But now in this case we have an extra trip between I and J, so we have an extra cost of Cij. So we subtract this extra cost from our saving and we obtain our total saving if we link customer I and J in the same link. And we calculate this Sij for each of the customers. For example, if we have n customers, then we will have n2 combinations for Sij total number of Sijs will be n multiplied with n minus 1 divided by 2. And this number, this is a number that we can cope. If the number of customers is 100, then we will have 5000 Sij values. So we can easily calculate this 5000 Sij values and apply the methodology. To apply this methodology, what we do is to sort the Sij values from the highest to the least one. And we start from the highest value. We check the highest value and combine those customers in the same link. And then we check the second highest Sij value and again we combine those customers in the same link until the links violate feasibility. How we can violate feasibility? For example, trucks may have capacities. So we may add new customers to a link until the capacity of the truck lets. Now I will show you an example and the methodology will be more clear for you with this example. In this example, we have 5 customers and the location of the customers are given here. The location of their x-axis and y-axis are given. And here the daily requirements of the customers are given. In the example, there is a bakery and this bakery delivers loaves to the customers. And there are 5 customers, as I mentioned. Here on this graph, we see the location of the customers. Here we have the daily requirements. We have to calculate the distance between the customers and the bakery, and also we have to calculate the distance between each of the customers. So first we will calculate these distances. And for this, we will use the straight line or Euclidean distance between the points. What we will do is to subtract the x-axis, take the square, sum it with the difference of the y-axis square. And then we will take the square root of this summation to obtain the Euclidean distance. Here is the table which indicates the distances between the customers and also from the bakery. Now we will calculate the Sij values and here we calculate all the Sij values. What we do is to sort these Sij values from the highest to the least. And when I check the highest value, I see that S12 has the highest value. So I will add the customers 1 and 2 on the same link. By the way, I forgot to mention the trucks have capacity and the trucks can carry at most 300 of loads. By the way, we also know the demand of each customer. So if I combine customers 1 and 2 on the same link, here I know the requirements, I sum up their requirements and I check if I violate the capacity constraint or not. When I check this, I see that the total is 247 loads and the capacity was 300 loads, so I do not violate the capacity constraint, so I can add the customers 1 and 2 on the same link. I continue checking the SIJ values, and second highest SIJ value is the S13. So now I will consider adding the customers 1 and 3 on the same link. I already added customer 1 with customer 2 on the same link. So now I will check if it is possible to add customer 3 on the same link with customers 1 and 2. Now, total capacity that I used with customers 1 and 2 is 247, and I checked the demand of customer 3 and I see that that is 26. So I check if I add this capacity, if I violate the feasibility or not, and I see that it is 273. So I see that it is still feasible. So I conclude that I can also add customer 3 on the same route with customers 1 and 2. And now I continue checking SIJ values, and now the highest SIJ value is the S23. But now I know that I already added customers 2 and 3 on the same route, so I disregard this SIJ value. And now I see that the highest SIJ value is S15. Now I will check if it is possible to add customer 5 to the route of customer 1. The demand of customer 5 is 110, and on the previous route that we created, we already used the capacity of 273. So if I add the demand of customer 5 to this capacity, I will exceed the capacity. So the link will become infeasible. So it is not possible to add customer 5 to this route. So the next feasible pair on the list is 4-5. Now I will check if I can add the customers 4 and 5 on the same link. Let's check the demand of these customers. One of them is 140, the other one is 110. So when I add these two customers on the same link, the total capacity that I will use will be 250. So I do not violate the capacity constraint. So it is possible to add these two customers on the same route. So I created two routes with two vehicles. One of the vehicles visit the customers 2, 1 and 3, and the second vehicle visits the customers 4 and 5, as you can see on this figure. And this is the solution for this problem with this methodology. But of course, this is not the optimal solution. I mean, this is not the solution that minimizes the total distance. This is an heuristic approach, so we cannot guarantee that the solution that we found is optimal. To be able to find the optimal solution, we can formulate a mathematical formulation for this problem. And for such a problem, it is really easy to solve that optimization problem and obtain the optimal solution. But when the problem size gets larger, I mean when the number of customers increases, then it may not be possible to solve our mathematical formulation optimally. For that reason, we introduce you such heuristic methodologies. Now I will talk about some practical issues in vehicle scheduling. We can classify vehicle scheduling problems into two groups, as arc-based and node-based vehicle scheduling problems. The problems that we already discussed are node-based vehicle scheduling problems. I mean, in these problems, the objective is to visit a specified set of locations, I mean nodes. But on the other hand, on the arc-based vehicle scheduling problems, the goal is to cover a certain collection of arcs in a network. And typical examples for this problem are snow removal and garbage collection. For example, think about garbage collection. When the garbage truck enters a street, it collects all the garbage on that street. And in that problem, the aim is to visit a certain number of arcs to collect the garbage. And also, in the snow removal example, to remove the snow, the truck enters a street and removes all the snow on that street. So the aim is to cover a certain collection of streets in that problem. As I mentioned before, most real-life vehicle scheduling problems are much more complex than the problems that we discussed. And now I will talk about some features that make the real-life problems much more complex. For example, the first feature is frequency requirements. In the previous problem, there was a bakery and we assumed that the bakery should visit the customers daily. But in real life, the frequency may change from customer to customer. Consider delivering oil or gas for residential use. The frequency of delivery depends on the usage rate. So the delivery frequency will vary from customer to customer. And also time windows. This means that the visits for the customers may be at certain specific times. For example, postal and bank pickups and deliveries are typical examples for time windows. And time-dependent travel. In the problems, we assume that the time between the customers or the distance between the customers are certain, and according to this distance, we assume that the time is certain. But of course, this may change according to traffic, for example. And traffic changes according to the time of the day. So according to the time of the day, the travel time may change. And also there may be multidimensional capacity constraints. For example, the capacity may be about weight and also about volume. And when we carry different variety of products, this may cause problems. And another feature that makes the problems difficult is vehicle types. In the problems that we discuss, we assume that there is a single vehicle type, but in real life, of course, companies may have several vehicle types, and according to vehicle types, their capacity, cost of operation may change. And when we have different vehicle types, the number of feasible alternatives increases dramatically. And split deliveries is another feature that makes the real-life problems difficult. For example, we may not make the delivery to a customer with a single delivery. I mean, we may have to split our deliveries, so we may have to assign more than one vehicle to a single customer. And lastly, uncertainty. In the problems, we assume that we know all the information, but in real life, of course, this is also not possible. For example, as I mentioned, we may not know the travel time. It may depend on the traffic, and in real life, we may have such uncertainties about the parameters of the problem. As I mentioned, one of the features that makes the real-life delivery problems difficult is uncertainty. And to mitigate this uncertainty and increase the efficiency of the system, we have a key strategy called risk pooling. Risk pooling means that when one adds multiple sources of variability, we can decrease the total variability of the system. One common measure of relative variability is the coefficient of variation. We indicate it with CV. And coefficient of variation of a random variable is the ratio of the standard deviation over the mean. If x is a random variable with mean mu and standard deviation sigma, then the coefficient of variation of that random variable x is equal to sigma over mu. Now we will talk about risk pooling. Assume that we have n independent sources of variation and we represent them with random variables x1, x2 and goes to xn. And assume that these are independent and identically distributed with mean mu and standard deviation sigma. Assume that a single retailer has n stores, and these n stores, each of them have a demand with mean mu and standard deviation sigma. And W is the sum of the demands at the n stores. Now let's calculate the mean and standard deviation of W. Since we assume that these x random variables are independent and identically distributed, we can easily say that the mean of W is n mu, and for calculating the standard deviation, firstly we calculate the variance of W, that is n sigma square, so the standard deviation of it is sigma square root n. So here is the coefficient of variation for W. I mean for the sum of the demands at the n stores, and here it is given with this formula sigma divided by mu multiplied with square root n. And from this formula we can easily see that when n increases, the coefficient of variation will decrease. So if n is sufficiently large enough, then we can decrease our variation of the system. Even the decision random variables do not have the same distribution, we will encounter the same situation. I mean, when n increases, the variation will decrease. And risk pooling is commonly used in finance for creating the portfolios. For example, we find financial products such as stocks and bonds, and when they are negatively correlated and when we have sufficient variety, I mean when our n is large enough, then the risk of the portfolio is decreased. And in operations management, the goal is to aggregate sources of uncertainty so that the whole is easier to manage. And there are three key versions of risk pooling that will be discussed, and they are inventory location pooling, product pooling and postponement, and lastly capacity pooling. I will start talking about risk pooling with inventory and location pooling. In inventory and location pooling, if there are several geographic sources of demand that can be served by the same supply, then pooling will mean that the aggregate demand will have lower coefficient of variation. Inventory pooling can be physically or virtually. What I mean with physically is that there can be a centralized warehouse that will serve each demand point. And what I mean with virtually is that there can be an information system, and with this information system, products can be transshipped from one demand point to another demand point. Now I will show you an example for inventory pooling. In this example, there is a toy retailer with two warehouses in St. Louis and Kansas City, and the warehouses stock an identical popular toy delivered to stores in two cities. And assume that a warehouse only serves to the store in its city. And weekly demand for St. Louis is normally distributed with mean 2000 and standard deviation 400. And weekly demand for Kansas City is distributed with mean 2000 and standard deviation 300. We assume that two cities are far enough apart so that demand in two cities is independent. And also we have the following parameters for both warehouses. Replenishment lead time in weeks is normally distributed with mean 2 and standard deviation 0.1. Fixed shipping cost of replenishment is $500. Cost of a toy is $10 and holding cost per toy is 20% of toy's value per year. And now the question is that how many toys should each location order at a time and when should they reorder if they want a 99% cycle service level? What if they pool the two locations? For this problem, first we will consider a decentralized system. I mean, we will assume that there will be two warehouses and these warehouses will only serve to the stores in their cities. And after that, we will consider a centralized system. I mean, we will assume that there is a single warehouse that will serve to both of the stores. And here, it is asking for a 99% cycle service level. Remember that when we discussed stochastic inventory control, we talked about type 1 service level. In that case, we assume that the probability of a stockout in a reorder cycle can be at most 1% when we want to satisfy 99% cycle 99% of cycle service level. Now, firstly, we will calculate the EOQ value. For the EOQ value, we need demand rate, fixed cost of ordering, and holding cost. And we will first calculate the demand rate yearly. The demand is given weekly as 2000 and yearly demand rate is calculated as given here. We know the fixed cost of ordering and we know that holding cost is 20% of the cost of the toys. Cost of the toys is 10 and 20% of it is $2 per year. And with the EOQ formula, that is square root of 2 lambda k divided by h, we obtain that the EOQ value is 7221. Now we will calculate the safety stocks for both of the warehouses. The EOQ value is valid for both of the warehouses because their demand was same. So we will use the same EOQ value for both of them. But since the standard deviation of the demand changes in two warehouses, the safety stock level will change. Now we have a service level of 0.01 because we want to satisfy a 99 service level. I mean, it is the probability of satisfying the demand in a reorder cycle. So with this 0.01, we use the normal table and we obtain the Z value as 2.33. We obtain the safety factor. And also here the critical point here is to find the standard deviation of demand during lead time. And here with this formula, we calculate this standard deviation of demand during lead time. And also the formulation is given in Excel sheet here. With this formulation, we calculate the standard deviation as 600. And for the safety stock, we multiply our safety factor, that is 2.33, with this standard deviation obtained, and obtain the safety stock as 1395.81 for the warehouse in St. Louis. And we make the similar calculations for the warehouse in Kansas City also. And also we calculate the reorder points by summing the safety stock with lambda multiplied with the MUTI, I mean expected lead time. And we calculate the reorder point. And now here we calculated the safety stock separately. We considered that there is a decentralized system, and also when we make the similar calculations for the Kansas City, we see that the safety stock is 1092. This time we will assume that there is a centralized warehouse, and now demand becomes 4000 and standard deviation or weekly demand becomes 500. And with these values, we will make our calculations again and obtain the safety stock and reorder point. And when we calculate this centralized system, we see that the company should order 10,199 toys at a time. There's a reduction of 29% when we compare this number with the decentralized system. Also, the company will keep a safe stock of 1,890 toys, and this is a 24% reduction when we compare with the decentralized system. Now I will illustrate inventory pooling with a different example. In the previous example, we considered type 1 service level requirement. In this example, we will apply the news vendor model. Now assume that there are n independent retail locations that stock the similar items. And here we have overage and underage cost. Remember that when we cannot meet the demand, we have an underage cost, and when we have excess stock, we have overage cost. And we were calculating a critical ratio for the news vendor model with CU divided by CU plus CO. In fact, this critical ratio is the fractile of the demand distribution. Now assume that demand of this item follows the same normal distribution at each store with mean mu and standard deviation sigma, and the demands are independent from store to store. Now with the critical ratio, remember that we were finding a z value. In fact, it is the value of the standard normal variate that corresponds to a left tail probability equal to the critical ratio. And when we obtain this z value, we are able to calculate the optimal order quantity as Q is equal to mu plus sigma multiplied with z value. And this is for each location. And here also we are able to calculate the safety stock with sigma multiplied with z value. And this is again for each location. And since we have n different locations, the total safety stock in the system is equal to n multiplied with sigma multiplied with z value. And this is a decentralized system. I mean, we keep our stock separately in each of the store. Now assume that we have a centralized system. I mean, we keep the stock of all the stores in a single warehouse. And now we will consider this case. I mean, if we have such a system, what would be the order quantity and the safety stock level? Now, assume that we keep all the inventory in this central warehouse and we are sending the products to each of the stores from this central warehouse. Now, we know that demands are independent normal random variables with mean mu and variance sigma square. And since we have n stores, then the mean will be for that central warehouse n multiplied with mu, and variance will be n multiplied with sigma square, and standard deviation will be sigma square root n. And now with the same formulation we will calculate the order quantity and the safety stock, and this time order quantity is here and safety stock becomes z multiplied with sigma multiplied with square root n. Now we will compare this safety stock with the safety stock that we obtained with the decentralized system. This is the safety stock that we obtained with the decentralized system, and we divide with the safety stock that we obtained from the centralized system, and we obtain that is square root n. It means that with the decentralized systems we keep square root n times square root n times more inventory than the centralized system. When n is small, maybe this ratio may not be so important, but when n is high, we see that the inventory level really increases with the decentralized system. So with this example, again we saw that inventory pooling is important to decrease the total level of inventory. Now I will talk about product pooling and postponement. We just talked about inventory pooling. It was the first methodology to reduce the negative effect of variability, and this is another method to reduce the negative effect of variability. Now, in fact, this is the differentiation or postponement of the final product, where the configuration of the final product is delayed as long as possible. I will explain this method with an example. In fact, the first application of this principle was implemented by an Italian company called Benetton. Benetton is a company producing fashion clothes, and in 1980s it was the world leader in the field of knitwears. And 60% of the products sold by the company are made of wool. And traditionally, wool is dyed before it is knitted. But Benetton company undertook a very different strategy. They dyed the knitwears after they were knitted. In fact, this strategy has a higher cost of the traditional strategy. I mean, in the traditional strategy, wools are dyed and then they are knitted and they become knitwears. But in this new strategy, firstly, knitwears are produced and after they are dyed. And this new strategy has a 10% higher cost of the traditional strategy. But why Benetton undertook such a strategy? Benetton included nearly 500 color and style combinations. And in each year, in each season, popular colors were changing. And to cope with this, instead of coloring them, they kept gray stocks. They produced the knitwears, but they didn't dye them, and they called this as gray stock. And they observed the demand. In each season, they observed which colors will become popular. And when they made their observations, and when they decided the popular colors, they dyed the knitwears. And with this new strategy, in fact, they get rid of the large unsold stocks of knitwears in unpopular colors. Product pooling and postponement can be applied in different industries also. For example, companies do not want to keep the inventory of the final product. Instead of that, they keep the inventory of the semi-finished products, and when they get the demand, they can easily assemble these semi-finished products or make the last operation of that semi-finished product and obtain the final product. This is also the postponement of producing the final product. And lastly, I will talk about capacity pooling to reduce the negative effect of variability. Most production systems require excess capacity for the fluctuations in either demand or supply. We call this excess capacity as safety capacity. But if capacity can be shifted among the products, different product demands are effectively one pool. In this case, less safety capacity is needed. However, flexible capacity is usually more expensive than the dedicated capacity. So, capacity pooling should be done very carefully. With flexible capacity, machines may produce different products. So, we need setup time for these machines. For example, we talked about the Toyota systems. Remember that we talked about single minute exchange of dies. For example, in these systems, in fact, there is a flexible capacity because easily we can do the setup and we can change the capacity of that machine to produce another product. In the service system, capacity pooling means that workers can be capable of doing more than one job. And this involves cross-training. And in fact, the workers may be more expensive because they need a higher skill set. So for that reason, again, the capacity pooling should be done carefully in the service system. Now here in the figure, you see that there are 10 products and there are 10 plants. If each of the product can only be produced in a single plant, we can say that that system is not flexible. In the second figure, you see that each of the products can be produced in each of the plants. This is totally flexible system. But in the first figure, we see that each product can be produced in 2 plants. So we can say that this is partial flexible. And the good news on capacity pooling is that its benefits can be achieved without a fully flexible system. The first system is almost equivalent to this second system, the system with total flexibility. And lastly, I will talk about multi-level distribution systems. In multi-level distribution systems, inventory may flow from manufacturer to regional warehouses, from regional warehouses to local warehouses, and from local warehouses to stores or other point of use locations. And to determine the allocation of inventory in these multiple locations is an important strategic consideration. Here in this figure we see a multi-level distribution system. We have a plant, we have 2 distribution centers, and we have 3 stores that are served from these distribution centers. Multi-level distribution systems have advantages and disadvantages, and now we will discuss these advantages and disadvantages. Let's first talk about the advantages. These are firstly risk pooling. Remember that when we talked risk pooling, we talked about a coefficient of variation, and this coefficient of variation decreases when the number of stores increases. Secondly, distribution centers that can be designed to meet local needs. Okay, think that in our plant we are producing clothes, and one of our stores is in Antalya and the other one is in Kayseri, and assume that the first distribution center serve to Antalya and the second distribution center serve to Kayseri. In that case, the variety of the clothes should change in these distribution centers. I mean, for Antalya, more swimming clothes will be needed, or for Kayseri, more clothes for skiing or snowboarding will be needed. And so distribution centers can be designed according to the need of the stores. And thirdly, the advantage of multi-level distribution systems is economies of scale in storage and movement of goods. For example, think about the movement of the goods. If we don't have distribution centers, then the plant will send the products to each of the stores, and the amount of products sent will be less, and probably the plant will use small vehicles. But when we use distribution centers, the amount of product increases because we consolidate the flow when we send to distribution centers, and probably the plant will use larger vehicles, and when we use larger vehicles for transportation, in fact we decrease the unit transportation cost. For that reason, when we have such distribution centers, we decrease the unit transportation cost of the products. And lastly, faster response time. Now, when we have such distribution centers, you see that inventory is closer to the stores, so we can decrease the response time when we have such distribution centers. And now the disadvantages of such systems. Firstly, these systems may require more inventory than simpler distribution systems, because now we have distribution centers and we have to keep inventory in those distribution centers also. So we may require to hold more inventory. Secondly, may increase total order lead times from the plant to the customer. Assume that there is a storage, there is a shortage in the distribution center. So when there is a shortage, first the distribution center will demand from the plant, and then the store will make a demand from the distribution center. So we have two different lead times now, lead time from plant to the distribution center and lead time from distribution center to store. So this may increase the lead time. Thirdly, could ultimately result in greater cost for storage and movement of goods. This may result because, of course, it is expensive to open such distribution centers. I mean, to construct these distribution centers or rent the building for the distribution centers. And also, there are workers working in these distribution centers, and also we have a cost to operate these distribution centers. So in the end, we may have greater cost for storage and movement of goods. And lastly, these systems could contribute to the bullwhip effect. Remember that the variation in the demand increases when we have levels in the distribution system, and such systems may also contribute to bullwhip effect. And that is all that I want to talk in this video. Thank you for listening to me. See you. Goodbye.